These are serve it to you by now. They don't give it to you like in a package. You just put it on your glass. If I didn't weigh it,
Oh, wow.
there was a guy with like glove nuts. It was tasted.
Yeah.
Yeah.
Okay, sad.
It's all over this giant oven. So we open the oven. It's like the size of this room.
Oh my gosh.
It takes the
Size of this room.
You go outside and it's like 90 degrees. The sun.
Oh.
Here it's more like gentle sun.
So it's still time.
So today is going to be a little like, the first half is going to be a little physics intensive, and then the second half will be more process. Okay. So Professor wanted me to teach about dielectric reliability and about high K and low K dielectrics. So there'll be a little bit about initially about dielectric physics, and then later on we'll talk about how to differ. Right. Okay, we can start. So, yeah, so actually, this Wednesday and Friday will be focused more on the project. Okay, so there won't be, technically, there won't be a lecture on Wednesday. So it'll be Vineet, me, and Krutikesh will be helping you with the project. So, since there's only 1 week, and Friday will also be the same. So, I hope, how many of you have actually made good progress on it? Okay. So by on Wednesday, we will give you a form, like a Google Sheet. So please enter your group, the teammates, okay? So and then I'll also send a Google Sheet to decide what 2 dates. So we need 2 dates next week because it's going to be 2 2-hour sessions for all the project presentations, right? So we need to figure out which days works for everyone, and then we'll have, and everyone has to be present for everyone else, okay? So it's not like once you're done the next class, you don't attend. So you have to attend for both. Because it's actually going to be, I don't know, it's like audience questions are important. So, make sure you come to class. Yeah, so we can start. So actually, I'm going to go a little bit about the physics of dielectrics in the first half of this class. And then the next half, I'm going to talk about how to deposit dielectrics, particularly high K and low K dielectrics, okay? So if everyone remembers, right, so there are mainly 2 kinds of dielectrics that we use when we do this entire CMOS process, right? So one is the high K dielectric itself. So imagine this is the gate. Oh yeah, still. And the dielectric that's used here for getting the gate controlled, and that is typically a high K dielectric, right? And the reason why it needs to be a high K is because you want to have good capacitive control in your channel, but at the same time, you want to make this thick enough so that you avoid other effects such as gate leakage, which happens when you make this dielectric thin. Then the second kind of dielectric material that's used is called low K, and that's typically used to fill the space between the, for example, say these are source and drain contacts and then metal lines and so on. So everything around it you want to be surrounded with low K. Okay, and the reason you want things to be low K for all the interconnects is because the interconnect latency, right? So remember that all the interconnects are just metal wires that go from one end to the other. And if you model them like using electromagnetics, right? They are primarily RC networks. So they are a bunch of resistors and capacitors. So how fast the signal is propagated or sent from one end to the other really depends on the value of these parasitic capacitors, right? So if you use a low K dielectric, you can essentially reduce this parasitic capacitance and you can send signals fast. So you want to have low K for all the interconnects and you want high K for the gate itself, right? So let's talk a little bit about polarization, right? So when you talk about dielectrics, one of the important concepts is polarization. So we need to understand, the microscopic origins of polarization, as well as how we can get, the main thing I want you to take away from this first lecture is, imagine you are actually a material scientist, right? And you had control over what kind of material you can make, a dielectric you can make. So I want you to understand how you can either increase or decrease dielectric, the value of the dielectric constant, just by understanding how the bond structure is or how the crystal structure is, right? So that's the main goal here. So if you look at the dielectric response, so what is the dielectric response? So a dielectric is a material that essentially, so it's some solid that when you apply an electric field, what happens is the electric field causes a polarization within this material, which means there's a charge separation. And so that this polarization creates an induced field within it that opposes the original field. Okay, so that response, the response to the incident electric field is what is called as polarization. So there are multiple phenomena of polarization that can happen. So first one is electronic polarization. So imagine you had an atom, so there's something like this, so there's a positive and there's a negative cloud around it. So if you don't do anything, right, the center of the positive charge, so the positive charge is center and the negative charge is center overlap. So this doesn't have a net so-called dipole moment, right? However, if I was to apply an electric field here, say I apply this kind of electric field, what ends up happening is the electrons are pulled towards one side because of the electric field. And because of that, now you have this deformed kind of a structure with the electrons being pulled to one side. So now this has a net dipole moment because the center of the positive and the center of the negative charge don't overlap. So this will start behaving as a dipole, right? And what is the consequence of that is, so for example, in this case, if you look at, if you had no electric field and you just consider this symmetric kind of a structure, if you look anywhere from outside, you don't experience any electric field due to this because it's completely charge neutral, right? However, in this case, when it is deformed this way, this actually generates now a dipole field, and that can interact with surrounding dipoles and so on. So that is basically the electronic polarization. Then you have ionic polarization, which happens generally in ionic and polar solids. So for example, if you take something like sodium chloride, right, salt. So there's an Na and there's a Cl minus. So if you apply an electric field, so imagine these things are just connected by springs, which is the ionic interaction. So when you apply an electric field, one ion gets pulled to one side, the other gets pulled to the other, right? And that creates a charge separation and polarization. And then the third one is basically orientational. So this happens, for example, in water, right? So if you take liquids such as water, it basically has something like, hydrogen and oxygen, right? So it has something like this, which is H2O. And what happens is because of the shape of this molecule, there's an extra negative charge here and an extra positive charge here. So this basically behaves as a dipole. And then when you apply an electric field, what happens is the water molecules tend to orient along the field, right? So imagine each one of these dashes are water molecules. When you apply the electric field, they start orienting in the direction of the field. So now, what is very general in all these cases, right? And this is a very important point to understand is, in all these kind of polarization cases, you essentially have some equilibrium position. And so say, take this case, right? There's a plus Q and then it's surrounded by minus. So this is the equilibrium position. And if I was to perturb, right? If I was to take this and move it slightly in this direction by some delta X or something like that, that perturbation will cause an increase in the energy of the system, right? So this equilibrium is the lowest energy. And if I were to perturb it, it will have slightly higher, right? So in any of these cases, there's a certain equilibrium position. So for example, this would be, this would be the equilibrium here, and this would be the non-equilibrium. So if you were to plot, right? So if you were to try to plot, what is the energy distribution, right? So it would have some kind of a complicated energy distribution as a function of the position of, whatever, right? And so about the equilibrium position, so for example, in this case, if this is the equilibrium position, then above this equilibrium position, there will be some kind of a minimum, right, in the energy landscape of this molecule, right? And so above this equilibrium position, what you can do is you can write a Taylor series of the energy. So the energy for any displacement with respect to the equilibrium is just going to be this. So it's going to be the energy at the minima plus these are Fourier series terms, right? So it's going to be the actual displacement times the first derivative of the potential and then second derivative and so on, right? And now if you are already originally at the minima, then the first derivative is 0, right? Because the minima had 0 slope, correct? So the first derivative is 0, and you just end up getting something like this. Everyone understands this, right? Yeah.
What are you perturbing about all?
No, so what I'm saying is like, let's say this is the original position of the molecule, right? Which means the center. So this negative cloud has a certain center, right? So the center of the negative cloud and the center of the positive, which is the ion inside, is coincident, right? But if I was to push this slightly so that the center of the positive is slightly pushed away from the center of the negative, slightly off center, that displacement is what I'm talking about here. But this is non-equilibrium. So if I was to magically pull this apart like this and then let it go and not apply any field, it will return back this original configuration, right? That's because this is the most stable configuration, right? So essentially, this molecule or whatever it is, it need not be this case, it can be any case, even the dipolar case. There is some energy landscape where it usually occupies the minima, but if you perturb it above the minima, then you can represent the energy at any of those perturbations as the scalar Fourier series, right? And so what happens is, yeah, so you have this, but in general, right, if your electric field is very small so that you don't actually rip everything apart, this displacement is typically very small, and so you can ignore these higher order terms, right? So if you look at this Fourier series, so this is the second order term, and then this is the actual perturbation from the original equilibrium, right? And if this perturbation is small, which means the applied electric field is small, then what happens? The higher order terms can be ignored, right? And so what happens is you just end up getting the energy very close to the equilibrium position is just the energy at the minima plus the second order derivative, right? And so if you remember, what is the relationship between force and energy, right? So if you had this configuration here, and say I was actually applying a force to this, right? I was creating this displacement by applying a force, then that force that I apply will have a basically an opposing force, right? Which is actually this configuration trying to come back to equilibrium, right? So that force would just be the first derivative of this energy. And so what ends up happening is you get, if you use this formula over here, you get F equals this times this, right? What is this? This is just this, Hooke's law. So this is F equals Kx, right? So essentially any molecule or, yeah.
So we're just treating the dielectric as like an ideal state.
Yeah.
Okay, so
I'm trying to explain why no matter what kind of energy landscape you have, if your displacement is small, it's going to always have Hooke's law dependence.
okay, so are we ignoring the higher ordered like potentially terms?
Yeah, we are ignoring it because the displacement is very small.
Okay.
So if you look at the operation of typical dielectric materials, right, they are not operated near breakdown. They are operated very far away from breakdown, which means this displacement from the equilibrium is very small. So you can assume the behavior to be like a Hooke's law kind of behavior. Okay, that's the main point. So everyone understand up to this point, right? So now think about, so what we're going to do, and this is typically what people do to understand how dielectrics behave is, you can model this entire, basically this dielectric, this kind of, in this case, this kind of electronic structure as some equivalent mechanical circuit, right? So in this case, imagine you applied a force, correct? So the force is the actual electric field. So what is the electric field going to do is the electric field is going to try to pull the negative cloud this side and the positive this side, right? But because it's pulled apart, it wants to return back to equilibrium. There's going to be a kind of a opposing force, which is actually the spring force, right? Which is the Hooke's law force. So now if you write a force balance equation, right? So if you do remember Newton's law, which is just mass into acceleration is force. So the mass into acceleration is just going to be mass times the second derivative of the displacement, right? That is equal to what are all the force components? So one is the force from the electric field itself, which is going to be the charge times the electric field. And then the other one is basically the opposing force, right? Which is because it wants to come back to equilibrium, which comes from the Hooke's law, right? Which is going to be K times this displacement. Plus, also, these systems also have a kind of friction, depending on how fast the displacement happens. There's also an extra force, which depends on the rate of change of position. And that is given by it's basically like a friction, okay? The faster they want to, you push the molecule back and forth, the higher is going to be this friction, and that's also going to add a force term to this force balance. Does everyone understand this? He's nodding his head no. Okay, see. This is the equilibrium, right? So there's a plus Q and there's a minus distributing thing, correct? It's okay so far, right? So if I wanted to pull these apart, right? I wanted to pull the negative thing to one side and the positive to the other. Think of this as the equilibrium position, right? Like think of this as a situation that the spring is not extended. The moment I pull these apart, that's like extending a spring, right? Which means it wants to come back, correct? So if I model this just as a spring, then this was the original equilibrium position. And then when I apply the force and pull the spring apart, there's a force I apply, but there's also a force that is trying to pull it back, right? That is a force that wants to bring the spring back to its original position, right? So that's the same thing here, but here the force that is applied is actually the electric field, right? So if there is some charge Q times the electric field is the force that's trying to pull this apart. And then there's the opposing force, which is the spring force that is trying to bring it together, right? So that's going to have a term K times R. And then depending on how fast you move this, right? So imagine like you had a syringe, right? If you take a syringe and move it slowly, you won't experience much force. But if you pull it very fast, you experience a large force. That's because the force in that case is dependent on the velocity, because it's a friction. Okay. So there's an additional friction term also depending on how fast this displacement comes. Okay. And this whole force is going to cause, basically by Newton's law, the force is m times a. It's the mass times the acceleration. Yeah.
Can you explain again what's the KR term?
Oh, this is Hooke's law. This is Kx. So this is a
KX.
spring. Yeah, essentially this thing is being modeled as basically a mass with a spring and then a dashboard.
What's the difference between the first term and the second? In that,
This term and this term.
the first,
This and this.
yeah,
This is the applied force.
yes.
This is a responding force, which is the spring trying to compress back,
Yes.
right? And depending on how fast you move, this is also a responding force.
I see.
Right? And this is just a force balance. So total force is equal to mass times acceleration.
Is it the mass of the atom or the charge?
No, it depends. Yeah, it's the mass of whatever is participating is being pulled apart, right? In this case, it's just going to be mass of this charge. You know?
So that's really nothing.
Yeah, exactly. So this mass will be this mass of this charge, right? Yeah. So now that's what I've written here. So imagine you have this chemical bond, right? So you have some positive ion here, some positive ion here, and you have some cloud around it, right? So the moment I apply an electric field, what's going to happen is these electrons, originally everything was equilibrium, right? They're equally distributed, so everything is charged neutral. When I apply this electric field, the electrons are pushed more towards this ion versus this. So it's going to develop this kind of a dipole moment, right? And so you can model this the same way I explained there by like a mass attached to a spring and dashboard, right? So now you can write this basically the force balance equation. So the mass times the acceleration, and it's very important here that the mass here is the total mass that is participating in the displacement, right? Which is in the actual number of electrons that is participating in the displacement times the mass of an individual electron. Not all electrons participate because remember an atom has multiple energy levels, right? So it is the electrons near the shell that is actually participating in the bond that participates in the actual polarization process. So that's why you only take those electrons Ne that participate in this kind of polarization process. So right. So this is mass times acceleration is the applied force. This is the damping because depending on how fast you are causing this displacement, there's going to be like a frictional force. And then this is the actual spring force that's trying to bring it back to the original position, right? So this is the force balance equation. Okay. So main thing to understand is how this arrives. So you understood how the force balance arrives and why you can approximate this very complicated kind of a bond structure with just a simple Kx. is because you're assuming the electric field is so small that no matter what the potential landscape is, near the minima, it's going to behave as a parabolic, and then you can use Hooke's law. So everyone understand up to this point, right?
That electron charge is not warm, right? You have to substitute with negative charge.
Which one?
The first term on the left, right hand side.
This one.
Negative, well, this right hand side, the first.
Yeah.
Yeah, that E has the negative in it.
No, that's negative is here.
It's already over.
Yeah. Yeah, so you can rearrange this, right? And this is just saying that, this is the, and, the spring constant, if you remember, right? So what is the meaning of the spring constant here, right? So the meaning of the spring constant here is it's telling you how stiff the bond is when you apply a field to polarize it, right? So it's very interesting that different bonds actually have different stiffness. That is the key to making a high K or a low K dynamic, okay? So some bonds, for example, a silicon nitride bond, actually has a very high stiffness compared to a silicon oxide bond, and that affects the way it polarizes. Okay, and so if you remember from basic mechanics, right? So the frequency, the natural frequency at which this kind of a resonator resonates at, the natural frequency is given by root k over m, correct? And so you can write k as m omega naught squared, where omega naught is the resonant frequency of this particular mechanical system, right? So that's what I've written here. So the spring constant, which is actually in this case is the bond stiffness to polarization, is going to be basically the mass, which is number of electrons that participate in the polarization times the mass per electron times this natural resonant frequency of this particular bond, right? Very much. So if I substitute that, you get this basically this differential equation. And what you can do is, you can see basically this is, in standard, any kind of mathematical analysis like this, what you can do is you can always do, and if you look at this as a linear equation, so it obeys superposition. So you can do a Fourier analysis, right? So you can consider that the electric field that's applied is time harmonic, right? So sinusoidal, and then you can see what the displacement response is, right? Which is also sinusoidal. So if you assume that the electric field is some sinusoid and the displacement is some sinusoid substituted here, then you get this kind of expression, right? This is the displacement as a function of the applied electric field, right? So as a function of frequency also. So depending on frequency, this tells you, given an electric field, what is the actual displacement of the bond itself. So far, makes sense? So yeah. So now that you know the displacement, right? So you know now what is the actual charge displacement. The dipole moment is just given by the total charge times the displacement, right? So the dipole moment is just going to be this displacement that we calculated times the total charge, which is Ne times E, correct? So this is the dipole moment.
So is dipole moment is for one of them or for?
No, this is just for one bond. We are going to go to many bonds.
So what did you at the end?
Oh, okay. So what this means is that so what is a bond, right? So if you consider what a chemical bond actually is, so there's two ions, let's say, each ion is some atom, right? And then what actually happens when you form a bond is when you bring them close enough, the last shells, right? The last shells are the ones that actually form the bond, but not the shells within, right? So when I say NEE, what I'm saying is that the Ne is the number of electrons that actually participate in the polarization. The remaining electrons are shielded away, they don't participate, right? It's only the electrons which are more in the outer shell that actually participate in the bond and the polarization. Yeah. Right now, till now, all this analysis holds only for one bond.
Can it be, for example, less than one?
Less than one as it?
Less than, for example, effectively less than one electron is participating.
No, it has to be like, no, it has to be more than. Yeah, so this is a dipole moment per bond, right? And now you need to go to from the per bond case to the bulk case, right? So imagine this is for one bond, but imagine you had n number of such bonds per unit volume, right? So let's say n is the number, capital N is the number density of bonds, right? Which is the number of bonds per unit volume. Then the polarization is just defined as a dipole moment per unit volume, the total dipole moment per unit volume. So you multiply the dipole moment of one bond times the number density of bonds to get the polarization, right? So this is the formula for the polarization. So far, so good. Okay. Yeah, always ask, like, you guys can ask me questions, like, yeah.
Sorry, electric field is different than original electric field, and we intended to apply.
No, this is the applied electric.
Then this electric field is the blend of what we intended to apply, and also the effect of the P, right?
No. This is just the electric field you applied. So the response, no. So that's the difference. You're thinking about the macroscopic effect and the microscopic effect, right? In the microscopic effect, this is the electric field that you apply. This is the electric field in the vacuum. Okay. And then this thing is generating its own field that opposes this field, and the net field inside a material will be different.
And the resultant electric field would be different than one.
Yeah, it will actually be lower than the applied electric. And so this is the polarization. Yeah. Oh, so gamma is just a friction. So like usually when you have so usually what happens is when you have like any kind of mechanical system, right? So when you apply, so consider a spring, right? So usually when you pull a spring, you apply a force and you have a spring wants to compress back. So that's a spring force. But also how fast you pull the spring also generates a force. Okay. And that's usually a type of friction. So the best place you can actually observe this is with a syringe. So if you take a typical syringe, right, and you try to pull it, you will experience a force as you pull it. But if you pull it faster, you'll experience even higher force because it's actually a friction that's operating, right? And so that's why also the symbol is like this, the dashboard, right? It's like a syringe, essentially, right? So this gamma term is telling you what is the frictional force. So imagine I was applying a time varying field, right? If I was constantly varying the electric field back and forth. So what's happening is this bond is going to this electron is sloshing back and forth, essentially. So as it is sloshing back and forth, that speed at which it is sloshing is also causing more energy loss, right? That is what is captured in this friction term, right? So this gamma is just a parameter that tells you how much is the friction of the bond sloshing back. And it's all empirical. So this gamma is empirically determined. Yeah. So we have the polarization. So now that we have the polarization from a microscopic standpoint, right? We need to get from this polarization what the dielectric constant is, right? And that can be understood from a macroscopic perspective. So in a macroscopic perspective, so imagine you had this kind of block of dielectric material, right? So when I apply the external electric field, what happens is all the dipoles are essentially oriented, right? So they're generating their own induced field that opposes the applied field. And so the net field inside is now lower, right? And so, macroscopically, the polarization is related to the electric field by this, which is called the dielectric susceptibility. And, if you remember from basic electrostatics, right? So D is epsilon times E, and there's a relation between the dielectric constant as well as the susceptibility, right? So if you just substitute the polarization in this, you get this kind of formula. And so you have basically the dielectric constant is related to the polarization by this formula, right? And now you just take this polarization over here and you substitute it here. And then from this, you can get what is the formula for the dielectric constant. So if you combine this and this, you get this formula for the dielectric constant of the material, right? So this is actually it's very basic thing. It's actually taught in many courses. It's called the Lorentz model. So it's like it's for low electric fields, it's actually a very intuitive way to understand how dielectrics actually behave with frequency, right? Everyone understood up to this? Yeah.
Easier in this case is just like the dielectric constant.
This is vacuum dielectric
Oh,
constant. Yeah. Vacuum permittivity. Yeah. Yeah, and so you now have this expression for the relative permittivity over here, and essentially, right? So this whole remember, if you substitute this here, what you can do is you can assume omega p to be this thing. It's just a parameter, right? It has the same units of frequency, so it's given by the number density of bonds per unit volume times the number of electrons per bond that participates times the square of the charge over mass of an electron times epsilon, right? This is also called as the plasmon frequency, okay? So this thing is what really determines it determines like the maximum frequency that the electronic polarization can actually respond to, right? But basically here what I've done is I've just grouped a bunch of things that has the same units of frequency and written it as omega p. And so, you have this expression for dielectric constant, and you can see immediately that this, because we assumed a time harmonic case, this is a complex number, right? And you know that dielectric constant is basically a real part and imaginary part. And then if you use basically this expression and simplify it, you can get what is the real part as well as the imaginary part of the dielectric constant, right? And so everyone understand this? Okay. For some reason, I don't believe that. Yeah, that's yeah, it's usually a convention. Yeah.
So, like, what's the significance of a real and imaginary dielectric constant?
So the real part of the dielectric constant determines the actual dielectric property, right? The imaginary part is actually the loss. It's represented dielectric loss.
Loss of what?
Loss of like you know the actual power loss, the dielectric loss, right? Because remember here you have this and that really comes from this term or the gamma term, because this is actually a dissipation, right? Some amount of energy is lost in the system, right? So if this was just a mass and a spring and I was to keep oscillating it, right, then no energy will be lost. But when I have a dashpot, it automatically dissipates energy, right? And so that is really captured in the epsilon r double prime, which is the imaginary part of the dielectric
It's
constant.
not a dominant factor in dielectric loss.
What?
It's the gamma
Mm-hmm.
dominant.
Yeah, that's why it's here. See? You see, the imaginary part is mainly dominated by the. So imagine gamma is 0, right? Then there's no imaginary part. Right? The gamma is the actual friction, right? So the gamma is the one that causes the actual dielectric dissipation. See, in practice, what actually happens is very complicated, right? It's like, so when the electron is sloshing back and forth, an electron that is moving back and forth generates radiation, right? So there's some amount of energy lost due to radiation. There's like a lot of phenomena that happens when the electron sloshes back and forth during the polarization, right? And all that effect of energy loss is captured in this parameter gamma. Okay. So yeah, so the friction is what determines the loss in the dielectric material. And you know, so if the friction was 0, then it would be a completely lossless case, and you'd only have a real dielectric constant. Yeah.
Is there a reason why we use one apostrophe and two apostrophes?
That's just notation. Yeah. Yeah. And so, you know, the main thing is if you plot the real part and the imaginary part of the dielectric constant, right? So what you notice is that the epsilon r, the real part of the dielectric constant, which is the actual dielectric constant that you talk about when you talk about high K and low K, it remains constant up to a certain frequency, but beyond some point, it starts going away, essentially starts falling. And then when you go beyond a certain frequency, which is the omega naught or the resonance frequency of that bond, it no longer responds to the field. So it starts behaving like as if it is air, right? Because the material is no longer responding to the field itself, right? And what you notice is that near this point where this cutoff is happening, near the point where it's transitioning from kind of this. If you guys remember like a simple mechanical resonator, right? So when you go very near to the resonant frequency, it starts vibrating a lot. That's the definition of mechanical resonance, right? So it's the same thing is happening here. Is over here you are at a lower frequency, there's less loss. But when you go near the resonant frequency, the bond is the electrons are sloshing back and forth at very high magnitude. So that's why the loss suddenly starts to shoot up near the resonance, right? And then beyond this point, the bond no longer can respond to this field that is moving back and forth. So it starts behaving as if the material is no longer polarizable. So the dielectric constant now becomes 1, which means it behaves like it is air. Right?
What about magnitude of that?
No, that I don't remember. I think it's in like for electrons, I don't know, could be like terahertz. I think it's like a surface plasmon resonance. You must know that, right? Yeah, yeah. It's basically the plasmon resonance frequency, which I think is in terahertz. I'm not very sure. And yeah, so the main thing here, right, is so if you look at this real part of the dielectric constant. So imagine you want to know what is the behavior at low frequencies, right? So omega tends to 0. So if you look at the dielectric constant, this you want to know this value. So if you substitute omega 0, you get this formula, right? So this, even though this actually, we did very simple analysis to get this formula, it actually tells you a lot about how dielectrics actually behave, okay? So what this is telling you is that the DC value of the dielectric constant is going to depend on the number density of bonds per unit volume times the number of electrons per bond that participate square over omega naught square times some constant, right? So what this means is that if you want to make a high K dielectric, right, a dielectric that has a high dielectric constant value, what you need to do is you need to make sure that the bonds are not very stiff, okay? So if you make the bonds not very stiff, then what happens? Omega naught reduces, right? And this goes up. Similarly, you need to increase the number of bonds per unit volume that participates in the polarization, as well as the number of electrons per bond that participates. This is how you go. So that is what makes hafnium oxide different from silicon oxide, because hafnium oxide actually has bonds that have a very small resonance frequency, so they easily respond to the field. Similarly, they have a large number of electrons per unit per bond that participates in the polarization. So, and that's what leads to hafnium oxide having a higher dielectric constant as compared to silicon oxide. Okay, so from this point on, if you understood exactly how this came about, you can also understand how you can make a dielectric a high K versus a low K. Okay. So everyone good to this point? I think this is the main expression that you need to kind of, get from this entire whatever we discussed about till now. And so, this is just some extra things I added just for completion is, you can have different kinds of material, right? You can have a dielectric that's homogeneous and isotropic, which means it's uniform everywhere, and also it does not have directional dependence. So when you apply the electric field this way or this way, it doesn't really make a difference, right? However, in that case, what happens is typically when you talk about any solid, it doesn't have just one kind of bond, right? So it can have an SiO bond, but it can have an SiN bond. It can have any kind of bond, right? Because a material may not have just silicon oxide. It can have, for example, if you consider SiCN, which is another kind of dielectric, it has silicon oxide, it has silicon carbon bonds, it has silicon nitrogen bonds, and so on, right? And each bond essentially behaves differently because each bond now has a different stiffness. It has a different number of electrons that participate in the polarization and so on, right? So in general, what happens is you can consider in a case-by-case basis. So for each bond, you can calculate the same formula, which is, if I remember right, yeah, this formula. So each type of bond will have this formula. And then for the entire solid itself, you just add this same kind of expression for each kind of bond that is present, right? So that's why in this case, you have a sum over M, where M represents each kind of bond in this particular solid. And each one would have its own plasmon frequency because it has a different number of electrons that participate in the polarization, as well as a different resonance frequency because each bond can have a different stiffness, right? And so if you were to plot the frequency behavior of this, and I'm sure you guys would have seen this figure, is that if you take a typical this kind of complex dielectric material, you would have multiple resonance frequencies corresponding to the response of each individual bond, right? So initially, it would have a large dielectric constant, but after some point, say one of the bonds no longer can respond, then the dielectric constant drops. And then as you go further and further, the more bonds fail to respond to the field, the dielectric constant gets smaller and smaller, and ultimately at very high frequency, it reaches air, basically, right? Everyone good?
So an example of the frequency range, the dielectric we're using a CMOS, that's I guess IO2 or
Actually, those frequencies are very, very large.
yeah.
Yeah, they are in like, I'm not sure what the exact number, but you don't operate anywhere close to those cutoff frequencies.
So we don't have.
Yeah.
But how about for case or case?
You care more about these things when you talk about very, very high frequency, like optical frequencies and stuff.
I see.
Yeah. But the main thing you care about for CMOS is actually this. You care about what the dielectric constant at low frequency is. See, when I say low frequency, I'm saying comparatively, right? I'm comparing the frequency to the resonant frequency of the bond, right? The resonant frequency of the bond is going to be so high that any usual CMOS operation frequency is nowhere close to that, right? That's why you don't really worry about this kind of cutoff frequency when you talk about an oxide, right? Or a hafnium oxide or something, because this frequency is so large compared to where you usually operate. And now, before I go to the next slide, let me just ask you, what would happen if this was the same kind of dielectric, but it was homogeneous, but it was not isotropic? It means in each different directions, you didn't see the same kind of bond, right? From one direction, maybe you saw a lot of one kind of bond because it has some kind of a structure, but in another direction, you see different number of bonds. So what happens in that case? Exactly, yeah. So then in that case, each direction has a different behavior, right? So then you'll have the same formula, but on each kind of basis direction, right? X, Y, or Z direction. So in that case, it'll end up being a matrix, right? And then what about a case where, and this is important for the low-K dielectric later, what about a situation where you had a material that was not homogeneous, right? So you had a whole bunch of different dielectrics kind of mixed together, different regions with different dielectrics throughout this volume of this material, right? If these dielectric regions are very small and the frequency is not very high, what you can do is you can just take a volume average of the entire dielectric constant, right? And later we'll see why this is important, because one of the ways to make low-K dielectrics is actually to make the dielectric porous. And what you do by making it porous is you increase more places where there's air inside the dielectric, so that the effective dielectric constant now reduces less than the original medium's dielectric constant.
Is this the same case with the gate that we are using? Because like we deposit we also like
Yeah.
it's the same case.
No. No. But it is amorphous doesn't mean the dielectric constant is varying with. It's still homogeneous. It's not inhomogeneous.
But if the crystal structure is
Mhm.
like it's also
Yeah, but those variations are so small that it just averages out. You know what I mean? Like, see, if you get pure same kind of behavior, same kind of epsilon throughout, right? But versus you have slight variations, but those variations happen within such a small length scale that it just behaves as some average dielectric. You know what I mean? That's why here you see this is only applicable if the volume of each region is smaller than the overall volume, much smaller, right? And the frequency operation is much smaller than the stiffness frequency. And then, this is more relevant to the, to your design in the transistor, is what happens when you have like the electric field in one direction, but then you have multiple dielectrics, of different thicknesses sandwiched, right? So in this case, it's just a bunch of capacitors in series. And then what you can do is you can calculate that essentially if this whole thing was going to behave as one oxide of particular thickness, you can use this formula. Basically, you're just saying that this is a series capacitance, so you take the reciprocal and add them, and then equate them to the capacitance, assuming it's all oxide. And then from this, you can calculate the equivalent oxide thickness, right? And this is something you would have done for the project. So imagine, and the reason why you do this is because, say, for your scaling, right, you wanted to go to 1 nanometer oxide to get the behavior of the transistor that you want, right, when you do density. But if you do 1 nanometer silicon oxide, the thickness is so small that it's going to have a large gauge leakage, right? So you want the behavior same as a 1 nanometer oxide, but you want to use a thicker dielectric. And the way you do that is you use, so rather than using a 1 nanometer oxide, you would use, actually 1 nanometer is too small, let's say 5 nanometer oxide. You would use like a very thin oxide, say 1 nanometer oxide, and then you'll use a larger thickness of something which has a higher dielectric constant, hafnium oxide, right? And so this stack, based on this formula, would behave the same as this, but you get the same kind of gate control, but with a larger thickness, right? So this reduces your gate leakage. So that's the whole concept of using multi-layer gate dielectrics to get the scaling. And that's why you use also high gate dielectrics. Everyone good? Okay. Yeah, so there are also like a lot of other behaviors, and this is really important when you talk about dielectrics, is there are a lot of trends you can observe with dielectrics, okay? So one of the examples here is, as you go to a dielectric with a higher dielectric constant, what you observe is that the energy gap is actually reducing, okay? The band gap is reduced. Similarly, as you go to a higher and higher dielectric constant, what happens is that the breakdown strength of the dielectric also reduces, which means dielectrics which have a higher dielectric constant tend to have actually a smaller breakdown. Okay. So can anyone think of why that would be the case? Like, why is it the case that the higher the dielectric constant is, the smaller the band gap is, as well as the more easy it is to break down? So you can understand it again from, yeah. So let me write down this. And some constant. So from this expression, right, which we derive from like very basic understanding of these kind of systems, can you explain from this why it is the case that, or why is it the case that when you go to higher dielectric, your energy gap reduces and the breakdown? I mean, if the energy gap reduces, obviously the breakdown will reduce, right? Because smaller energy gap would mean it's easier for the material to break, because it's easier for the electrons to go from the valence band to conduction band, so it's easier for it to break, right? But why is it that the energy gap reduces as the dielectric constant increases?
Yeah, it is higher. It's omega naught is lower.
If omega naught is lower, correct.
So when the omega naught is lower, it resonates sooner. That's
Yeah.
what makes the difference.
Yeah, so if you want to correct, yeah, if you want to increase epsilon r prime, right, you need to essentially lower omega naught. So what does lowering omega naught mean? It means that you are essentially making the bond more relaxed, right? So what does making the bond more relaxed mean? So, okay, imagine you have two atoms separated by some distance, right? So if you bring them closer and closer to each other, the band gap actually increases, right? That's how when you take basic solid state physics, right? That's how you have something called the tight binding model. It says that if these atoms are separated, right? So they have some electronic structure. And then as you bring them close, so initially each atom would have some kind of electronic energy states, right? But then as you bring them closer and closer, these energy states actually split like this. And then some of them overlap, but some of them don't overlap. And this is the band gap, right? But as you reduce the spacing, the band gap is actually reducing, right? That's essentially what's happening, right? So yeah, so basically that's what I've said here is like, as you reduce, it's because of the smaller bond length, right? So the way to increase epsilon r is to reduce omega naught, which means you are essentially making the atoms far apart. You don't want a stronger bond, right? So when you make them far apart, what happens is the energy gap is actually reduced. You understand what I mean, right? See, to increase epsilon r, you reduce omega naught. So if you had two atoms that are very tightly placed with each other, right? So imagine you had two atoms very close to each other and there's a spring. This is going to have a much higher stiffness compared to something that is further away, right? This spring is going to have a much higher stiffness than this spring, right? So a higher dielectric constant would have a low omega naught, which means the bond length would be larger, which means that the band gap would be also larger, right? Because they are further apart from each other. That's one way to understand like what.
So you said because they're farther apart, so their band gap is larger.
No, smaller. Band gap is smaller.
Band gap is smaller, so it's more the. And
Yeah,
it's more
if you take two atoms and you bring them closer,
Uh-huh.
the band gap is getting bigger and bigger, right? That's always the case. If you bring two atoms closer, the band gap is going to go bigger.
But how about, for example, like gallium nitride?
Mhm.
It's that is constant is larger than silicon. Base gap, band gap is larger.
Is that true? Is gallium nitride,
That is constant, yeah, bigger than,
it's larger than silicon?
yeah. It's how you learn it,
But also it is compound, right? I don't know how it works for compound.
but like the general trend is that if the lab is constant, it's larger for silicon. Band gap is larger, from what I know.
No,
Like,
the,
no,
the
no,
last one
opposite,
is smaller.
opposite. Yeah,
than the
yeah,
last one.
opposite.
See, it's basically it's the same. It's the way the band splits, right? So if you bring them closer, the band gap is going to go up. Actually.
Yeah,
Because the splitting increases, right? So it's going to go in. See, if you want to increase the dielectric constant, right, you need to reduce the stiffness, correct? You need to lower this frequency, which means you go to a larger beta atomic space, which means what your band gap is actually reduced, right? And so if you go to a larger dielectric constant, your band gap is reducing, which means it brings down faster.
okay, so why is dielectric with higher K is easier to?
Yeah, so that's what I explained here. Right? Look here, if you want a higher epsilon R, you need to lower omega, right? What is omega naught? It's a resonant frequency, right? So how do you lower the resonant frequency of mechanical resonance? It's by making the spring less stiffer. If the spring is more stiffer, it'll have a higher resonant frequency. Okay, that's why, for example, you take a, if you remember tuning forks, right? With the tuning fork, you remember tuning forks, right? The thing that you hit and then you get a sound. So the shorter it is, the higher pitch it is. The longer it is, it has a lower pitch, right? The reason is because the shorter it is, basically it's having a higher oscillating frequency, resonant frequency. And the longer it is, it has a lower frequency, right? In the same way, if you want to lower this frequency, you need to basically make the bond larger, the bond length larger, right? What happens when you make the bond length larger? If you make the bond length larger, you're actually reducing the band, right? You're reducing EG, right? And that's why when you have a higher dielectric constant, you essentially lower the band gap, and hence you have a much sooner breakdown. You have a much easier breakdown versus if it's a lower dielectric constant. Does that make sense? You don't agree. Okay, anyway, let's continue.
Your dielectrics to get the benefit of both.
Sorry?
Your dielectrics to get the benefit of both.
Yeah, that's what you do in this case, right? You layer the dielectrics. Yeah. Because you want an effectively higher so when you do this, okay, let me ask you, why do you do layered dielectrics? Why can't you just use high K?
Sometimes the breakdown.
No. So I'm saying you can, when you do the EOT, right? You have the oxide which is too thin. Why don't I just use hafnia? Why do I need this oxide also? Yeah.
Try and like on with the angular parts of the.
Yeah. Silicon always needs to have oxide first, right? That's how you passivate the dangling bonds first, right? So this oxide always has to be there, and then you put this hafnia on top so that the effective dielectric constant of this effective thickness, right, has an EOT, which is what you want, which is the finite. Yeah, so basically you have a bunch of, high K dielectrics, and then you have low K dielectrics, and, and obviously I'll upload this document so you can look through it. So you have various varieties of possibilities, and there are many reasons why people went with hafnia. One has to do with the ease of processing. It has a relatively high dielectric constant, And compared to other dielectrics, actually, it seems that, Hafnia actually has a better long-term behavior compared to when you use something like, for example, tantalum oxide for the high K. Right? And then with the low K, I will get to it once I talk about the low K process for the next half of the class. So now, once we talked about dielectrics, now let's talk a little bit about breakdown mechanisms of dielectrics, right? So we talk about how dielectrics fail, right? There's two kind of failure mechanisms, two main kind. There are many, many failure mechanisms, but I'm going to focus mainly on two kinds of failure. So one is an instant failure, okay? So the instant failure happens when the electric field is higher than the breakdown field, right? And then there's a time-dependent failure, which is called time-dependent dielectric breakdown, which can happen at a field which is lower than the breakdown field. Okay, so what usually happens in this this is called catastrophic failure. So if the electric field is close to the breakdown or higher than the breakdown, what happens is the electrons that come, so basically when I apply a field, there's going to be some electrons that's moving here, but this electron is going to gain so much energy that it's going to hit another atom, generate more electrons and so on. And then you basically get like a chain reaction. And then you get this whole region then becomes conductive, and then you short both sides, and that completely destroys the dielectric. Right? And that happens when you exceed the breakdown field of this particular dielectric. And then this is what is called dielectric breakdown, right? And then there's a second process which is called treeing. So you can see this is an example of this kind of dielectric breakdown, where there was actually an ESD event that happened and the field exceeded this breakdown field, and then you have this kind of instant breakdown of the dielectric, right? The second one is called treeing, which is a more gradual process, and it happens over time, and it happens at a field much lower than the breakdown field. So what happens here is the field is lower than the breakdown field, but what we will see later how this actually works is over time, you get this kind of a tree-like pattern that slowly over time goes and shorts both ends when the dielectric fails. Okay, and here this is a real-world example. Here, this is actually a piece of wood that people have connected to electrodes to. There's a little salt water on the surface to increase the conductivity, and you can see how over time, like the tree slowly forms, right? And people actually make art with this. So yeah. Yeah.
Down, you just have to throw it away as a recoverable.
No, these are not irreversible because it completely damages the dielectric, right? So what actually happens is, so once the breakdown happens, right, it actually kind of melts the dielectric, and so you get like this whole air, you get like a channel of air between. So it completely destroys that. So, this one is pretty easy to understand when you exceed the field, there's basically an avalanche effect. And then, the dielectric completely breaks down. But how do you, how do you understand time-dependent breakdown? So in most of the applications in CMOS, provided you can protect against ESD events, right? You care more about this time-dependent behavior breakdown. So how does the dielectric behave over time? And you want to characterize something called as MTTF, mean time to failure, which is one of the things that is used to characterize how reliable a dielectric is, right? So now, we're going to try to understand where this tree actually comes from, okay? So if you look at, so I've put here like a general understanding of how people model treeing. But the models can get very complicated, but fundamentally, right, the way you model treeing is, and the way this phenomenon actually happens is, it happens with something called as Bayesian random walk, okay? And it's actually very simple to understand. So what happens is, imagine this is a dielectric, right? So you have some dielectric in between electrons. So what you're going to do is, when a field is applied, so depending on the value of the field and the temperature, you have a certain and you divide this entire thing into a bunch of pieces, so there are a bunch of square pieces. What you initially, before you start, right, you assume that any of these square pieces has a certain probability of breaking down, okay? And then you play a kind of a game. So once one breaks down, the probability that others surrounding it can break down actually increases, okay? So you have something, if you remember from like your school days, there's something called dependent probability, right? So the probability that, say you consider the ijth cell. So imagine this is the I, jth cell, right? So the probability that a cell adjacent to the ijth cell can break down is going to be smaller than the probability that that particular cell breaks down if there was no cells around it that broke down. So what that means is that if there's a breakdown here, it's going to essentially cause the probability of breakdown next to it to be higher. Okay. And so over time, what you'll see is when you use this kind of a model to model this thing, you'll see that it actually gets this kind of a tree-like fractal pattern. Everyone understands this, right? This kind of algorithm of how you study this kind of breakdown. Over time, dielectric constant. No, see, the dielectric constant doesn't change. It's just what happens is certain regions of dielectric break down, but the entire dielectric doesn't break down at one shot, right? So a certain region breaks down, and then over time, the region next to it breaks down, and slowly it progresses all the way from one side to the other.
So it's like zero, where it's either like, it only changes once like all of it.
No. As it breaks down also over, like it does affect the behavior of the dielectric, yes. Yeah, of course. Yeah. Because you're kind of replacing a certain region with air, essentially, right? As you break down. So like, imagine that you're doing this game, right? And then it broke down here, and then next one here, next one here, next one here. Then you have this region essentially is now behaving like air, right? And slowly over time, your dielectric is failing. It's becoming worse and worse, right? And eventually it shorts out of it, right? And so using the same kind of algorithm, but this probability, right? The probability that one here breaks down when one here breaks down, that really depends on what kind of model you use, right? So that really depends on the actual physics of how it happens. And there are many models that tells you how to calculate this, the probability that one box here fails when a box adjacent to it fails, right? And also the initial probability that any box fails also depends on the electric field and temperature, right? And that also really depends on what kind of model you use, okay? And so here's an example of a simulation. So you can see based on this kind of model of how the treeing happens. So you can see how these are actually individual boxes that are failing. And you can see over time when you do this kind of Bayesian random walk, how the actual dielectric treeing is happening, right? In going from one plate over here all the way to the bottom, right? And so if you look at, after it's finished, you get this kind of tree-like structure. So it's a purely statistical process, right? So now if you were to actually do model mean time to failure, right? What you do is you take the simulation and you run it n times, okay? Each time it's going to, so the progress here, right? So the progress here happens in certain time steps. So the first time step, say this fails. Second time step, this fails and so on, right? So after a certain amount of time, this has gone all the way from here to here, right? So you repeat the same experiment n times and you get a distribution, basically a Gaussian distribution of the time it takes to fail in each case, right? And then the mean of that is called as the mean time to fail. Okay. So if I was to take any samples of the same thing and repeat the experiment, each one is going to have a different time that it takes for this thing to reach here, right? Because it's a purely statistical process. So if I plot that in a histogram and I find the mean of that, that is called as the mean time to fail. Okay. So yeah. So if you look at, so this is like, this is if you plot, for example, the time to failure versus the number of samples for n samples. So this, you get some kind of a Gaussian distribution, and the mean of that is what you take to be the NTD of the mean time to failure, right? And you have many empirical models for this. You can refer online. So usually the mean time to failure is obviously going to depend on temperature. It's going to depend on something called the activation energy for that particular region to fail. And it's also going to depend on what is the applied electric field, right? And here you see this is how you kind of generate this kind of plot is for each electric field, you run that experiment n times, right? So for each value of the electric field, you do that random process n times and you compute what is the Gaussian and you take the mean value and then you plot it, okay? And then you get this plot of the time to failure versus the applied electric, right? And what you want to do is you want to make sure that in the electric field that you operate at, you want to make sure that the mean time to failure is more than 10 years. So that's usually a kind of a parameter that people use when they talk about reliability. So they want to make sure that the dielectric remains relatively stable or it fails after 10 years for the electric field that it usually operates at. Okay. Is everyone good? Okay. We can take a break. Yeah.
For high data, we would use electron movements.
Yeah. That's the main reason because the gate leakage is mainly dominated by the tunneling action. That's why. And if you know from basic quantum physics, right? tunneling exponentially depends on the barrier width, right? So as the barrier width reduces, it's going to exponentially grow up the gate current.
I'd like to hear more about the time first failure versus time.
Time when the first failure occurs, isn't it?
Failure means that there are half of the devices are. So let's say fail.
No, that's why you say 10 years. Most devices don't operate for 10 years, right? So if your mean time to failure is 10 years, that means within 3-4 sigma, it's still going to operate for like, typically how long do electronic devices operate, right? You use them for like 3-4 years, not 10 years, right? Also, the experiment is done accelerated. So you would run the experiment at a much higher electric field and temperature that you usually operate at.
Yeah, no, I think that's what there's also the retail as how far it is on the end. We need to. There's also waiting. Yeah, so the probability that so say you start in the probability that like some years would actually higher than there's a distribution also initially. It depends on the model. I just want to show. Yeah, so you can have one tree that's running here, but you can also have one next to it. And all of them can combine, you know, in views. But the main idea is when one tree starts, it tends to propagate this way, because when one thing fails, the thing next to it has a higher likelihood.
Yeah, that's fine.
They could, yeah, it's completely random. That's the project. Yeah, of course. Yeah, I'm just because when I think like this, design the models that kind of determines the content, you know, and it also determines the content, so it's going to affect your Hi there. But I think you have yeah. Let's see. So you can either create your own videos or create with our solution. I mean, that's a different kind of silicon, but you can use this for.
But we can.
I think the issue you're having is both polysilicon and.
Yeah.
So it's actually both.
Yeah, I was actually both. Okay. Also, I wanted to ask, where did you find the video? That was, yeah.
Otherwise, you so if you and it gives you the location. There's some wild vibration that you have all your
What is?
this is for an open activation. This is for driving the web.
We don't need this one.
Yeah, actually, they're both the same. Just
Oh.
the
Okay, okay.
I feel like
So, Ian, which also not like a research day to be involved in 13, so from 12 to 14. And then
yeah, sure. I mean, I have to send out one now. And then it's actually, yeah. Yeah, so when you do that,
As many the SPC.
Then I use
So for this part, do we just like we just choose the polysilicon when I have these, right?
Yeah, correct.
And then you also need to choose like what dopant that need to drive.
What do we do?
I see. What's the last one?
Okay. Okay, let's begin. Okay, let's begin. So yeah, so till now we talked about dielectrics, reliability, and so on. So next, I want to shift gears and talk about how to actually deposit dielectrics, right? So how to deposit high K as well as low K dielectrics. So the way you deposit high K dielectrics, as you know from the process class, is something called atomic layer deposition. So actually, has Subbu taught ALD? He didn't tell you. He hasn't taught ALD, right? Okay. Okay, so as the name suggests, right, atomic layer deposition means you are depositing actually one atomic layer at a time, so one molar layer at a time, right? And the key thing why people use ALD is because ALD actually gives you very good control of the quality of the film you deposit, as well as it gives you angstrom level control of the film thickness. And also it is very, very conformal because it's also a CVD process. So you can see here, if you have some feature, if you do ALD, it really goes and it kind of conforms to the feature itself. And the way ALD works is it's basically similar to a chemical vapor deposition. So it happens in vapor phase, but however, it uses something called as half reactions. Okay, so the way it works is very simple. So the entire process is divided into a bunch of cycles. Okay, the more the number of each cycle, you actually deposit a molar. Okay, and so by having a certain number of cycles, you can deposit a certain fixed thickness of material onto your substrate, right? And each cycle itself is basically divided to a bunch of so-called half reactions. Okay, the first half reaction is called as a precursor reaction, and the second half reaction is basically called as a co-reaction. Okay, and then each A and B together is called one cycle. So, for example, what happens is in one ALD cycle is initially the precursor comes and gets adsorbed onto the surface. And then the co-reactant comes and bonds onto the surface, okay, thus forming one molar layer. And then this keeps repeating with each cycle. And so you can grow the material one layer at a time, okay? So for example, here you can see one of the very first ALDs was that of alumina. So to do alumina, you use something called PMA, called trimethyl aluminum, right? So it's basically an aluminum in the center with three methyl groups around it. And so what happens is, say your initial surface has some oxygen dangling bonds, right? So this aluminum comes, the aluminum attaches to the oxygen, and then you have this methyl group sticking out. So this is the first half reaction. In the second half reaction, what you do is you actually expose to like water, some kind of water or oxygen plasma, and then the methyl group actually goes away, and then you end up getting an aluminum oxide, okay? And that completes one molar layer of aluminum. Then the next cycle, you expose it to trimethyl aluminum, it comes and bonds to the oxygen, and then you keep repeating that process to grow the aluminum oxide one layer at a time. So here's like a quick video of how an ALD.
Atomic layer deposition, or ALD, is a process which can grow high-quality thin films using a binary sequence of half reactions, each depositing an alternate material at low pressure. ALD has the unique property of having self-limiting reactions, which allows for precise growth control over complex structures. Precursor molecules.
And one of the important things is a reaction can only happen when there's an exposed oxygen surface, right? Which means it is self-limiting. So what that means is the moment the entire surface is covered with these methyl alumina, the reaction stops. It doesn't deposit anything on top of it, okay? And then in the second reaction, again, each time it happens, it only happens as long as the surface is completely reacted. And then once the surface is fully reacted, it stops automatically. Yeah.
How does it sense it? Whether the layers.
No, it doesn't sense it. You do a certain amount of time. So if you do it too short, then it doesn't cover the entire surface, right? You do it long enough that, so that's why if you look here, right, there's like a saturation point, you know, you kind of start this process of exposing the gases, and after some time it saturates, which means it's covered completely the surface, but beyond that it doesn't grow further, right? And then the next step again you do, it covers the entire surface and so on. But it's self-limiting because once the surface is covered, it doesn't deposit anymore, right? That's how you get that atomic level control.
Atomic layer deposition. ALD has the unique property of having self-limiting reactions, which allows for precise growth control over complex structures. Precursor molecules are delivered by an inert carrier gas and will react with all available surface sites, after which the reaction terminates and excess material is purged from the system. This occurs for each precursor type, resulting in the growth of a single atomic layer. This binary process repeats itself until the desired film thickness is achieved. The properties of the ALD film can be optimized based on the different deposition conditions, including the material source and deposition temperature, which can be as low as 50 degrees Celsius.
Yeah, so you really get like one monolayer at a time control, right? And that's really how they, you know, when you look at all these transistors, they have oxides that are like, you know, few nanometers, right? And how they really do that is with this ALD. So this was the key technology to actually make those kind of features.
Atomic.
Yeah. No, it's as expensive as CVD. It's not very expensive. Actually, I have the world expert here in ALD here. Is it expensive?
But regardless, it's kind of,
But is it more expensive than a typical CVD?
it's expensive in CSI.
Okay. Yeah, and so, you know, these are some examples. And, you know, each type of dielectric that you deposit, whether it's silicon oxide, titanium oxide, or whatever, you have a different precursor chemistry, okay? And typically, you know, you have the precursor and then you have the co-reactant. The co-reactant tends to be the water or oxygen or ozone, and the actual precursor tends to be some very complex molecule in gaseous form, okay? So here you can see different dielectrics, and you can see how with the number of ALD cycles, it's basically growing a monolayer at a time. Right. And these are some common precursors for each type of dielectric that's used. So for example, methyl aluminum for aluminum oxide, and then this is for silicon dioxide, tantalum oxide, and so on, right? But this is the actual precursor, and then the so-called co-reactant generally tends to be the water or ozone or oxygen plasma. And, you know, if you look at a typical ALD equipment, right, you know, there's basically a chamber where the substrate is loaded, and then you send the gas in from one side. You also have this heater around it that heats the sample. And then once the deposition is completed for one particular half reaction, then you purge it. So you remove all the excess gas and material, and then you start the next half reaction. So on, right? And you have different kinds of ways you can do this. So this is one particular way that you send the gas in. You can also do it vertically. And you can also do batch process. So this is an entire container where you can load multiple substrates, and then you can do ALD in a kind of batch process. And so, you know, one of the things is, even though ALD is highly conformal, ALD is limited by, in the same way that CVD is limited, it's limited by something called as mass transport, okay? So what happens is, generally, right, when you have some kind of feature, so imagine you had this kind of a feature where, say, this was some silicon or something, and then say you had something else like this, and somehow magically say they have a gap in between, right? So if when you do ALD, you want to cover everything, including the space here. But what happens is, in order to cover the region here with ALD material, the gas has to go in all the way here, and then the product has to come all the way back, right? But however, if these things are very narrow, then what happens is the transport tends to saturate, so it doesn't go all the way inside. So you can end up depositing only here and not all the way inside. So even though it is conformal, it is still limited by mass transport. So if you have very, very fine features, sometimes the gas just doesn't go all the way down, because the gas has to go and the product has to come out, right? This is an issue in CVD as well. So, you know, it is still mass transport limited. And here's an example of a structure that you can make with ALD. So this is actually a so-called MIM capacitor, a metal insulator metal. So the way this particular structure is built is this is your transistor, and then on top of it you have this capacitor. Okay, so you have basically a bottom electrode with tinitride, then you have a top electrode, and in between them you can have some kind of, in this case, is zirconium oxide is used as a dielectric, right? And so using this, they've essentially made a kind of metal insulator metal capacitor, right? And so you can see here, this is the top view of the structure. Yeah, so that concludes ALD. All I have to say on ALD. Now let's go to low-K dielectrics, right? So if you remember this formula that I talked about earlier, right? So how do you make a low-K dielectric? So how do you lower dielectric constant, right? So one is you can obviously reduce N and Ne, which means you take a particular solid that is not that easily polarized, right? So you choose a non-polar dielectric system. That is a system that is very difficult to polarize. So that's one way to lower K. The other way is when you have this solid, you can intersperse a lot of pores within the solid itself, because remember, air has the least dielectric constant, right? It has dielectric constant of 1. So if a large volume of your solid actually has pores which has air in it, then your effective dielectric constant now reduces, right? So that's another way you can lower the dielectric constant of the solid. And then the third way is, third important thing to consider is you never want low-K dielectrics to actually have moisture, because water actually has a very high dielectric constant. In fact, the dielectric constant of water is around 80, right? So you want to make sure that these low-K dielectrics don't have any moisture in them, because that will increase the effective dielectric constant. And so these are three important things to remember when you make low-K dielectric. However, low-K dielectrics obviously have a lot of issues, because one of the ways that I mentioned to lower the dielectric constant is to lower N and Ne, right? So if you lower N is basically the number of bonds per volume, per unit volume, right? So if you lower the number of bonds per unit volume, what you're essentially doing is you're making the solid less dense, right? So if you make the solid less dense, what happens is its Young's modulus lowers, and so it's not mechanically as strong. So that's why a lot of low-K dielectrics, the moment you lower the dielectric constant more and more, they tend to have much poor mechanical performance. They tend to, break easily, right? So you can have a whole host of issues with low-K dielectrics. So they have, one of the things is etching them is very difficult. It's very difficult to get an etch chemistry that is very selective to the low-K dielectric. And also they have very poor adhesion to metals. They have a lot of mechanical and thermal issues. So for example, they can easily break when there is too much thermal mismatch, and also when you apply a lot of stress to them. Oops. So let's talk about the first way of trying to make low-K dielectric, right? Which is to lower N and Ne. So one of the ways is, so for example, if you take SiO2, right, silicon dioxide, it has a dielectric constant of around 4. But if you replace some of the oxygens with fluorine, so you have silicon OF, what happens is the so-called polarizability, right? Which means this number, Ne as well as N, is actually reduced. So the overall dielectric constant is actually reduced if some of the bonds are replaced by SiOF. You can also do it with carbon, so you can have SiOC as well. And then generally, right, the carbon bonds are generally have a lower polarizability as compared to silicon bonds. So that's why organics generally have a lower dielectric constant than silicon oxide or silicon-based materials, right? Because if you see most of the carbon bonds, the carbon-carbon, carbon-fluorine, and so on, they have a much lower polarizability as compared to like a silicon oxide or a silicon nitride bond. So the more carbon that you put into your system, the lower the dielectric constant actually is, okay? And so, here are some examples of low-K dielectrics. So you can have, organics obviously are going to be lower K than oxide because they're just filled with carbon and hydrogen and so on. And so, you can use these organics, which have a very low dielectric constant. And you can also make oxides themselves low K by adding some fluorine, carbon, or hydrogen into them, because you're lowering the polarizability of the bonds, right? And then you can also have a structure that is very porous, which are typically called as aerogels. I'm sure you would have seen YouTube videos of this. But this is basically filled with a whole bunch of voids, and it tends to have a lower dielectric constant. Yeah. That's silicon dioxide. Yeah. When you say oxide, it's generally silicon dioxide. Yeah. Okay, then yeah, and there are many ways to deposit low-K dielectrics. Typically, they're deposited by CVD, or you can also spin coat them, right? So, for example, materials like polyimide and organics typically can be spin coated. So they have some monomer dispensed in some liquid. You spin coat them, and then you bake them. It polymerizes, and then you get the organic polymer, right? And typically, when you have a K greater than 2.5 or something like that, you use CVD. And for even lower K, generally it is tend to be spin on, right? And here's an example of the first case is when you grow the silicon oxide, which is typically grown with this kind of silane, you add some kind of SiF4 to it. And what happens is when this deposits on the surface through the CVD process, some amount of oxygens are now replaced by fluorine, okay? And by controlling the percentage of fluorine in this particular oxide, you can control the dielectric constant. So here you can see how the intrinsic dielectric constant is changing with the percentage of fluorine, right? So as I increase the fluorine percentage, and what I mean by fluorine percentage is that's the number of fluorines that have replaced, is the percentage of fluorine that have replaced the oxygen in the SiO2 structure, right? So as I increase the fluorine content, you can see that I can modulate the intrinsic dielectric constant. But however, in this particular case, there is an issue, which is when you exceed the fluorine concentration more than 4%, this tends to soak up moisture, which tends to increase your dielectric constant, okay? So there's actually a sweet spot as to how much fluorine you can add in this case, which is around 4%. And that lowers the dielectric constant, but if you go anything beyond that, it also absorbs moisture, and hence it tends to actually have a higher dielectric constant. And then, you can always have organics. Organics have a whole bunch of carbon, carbon, fluorine, carbon, hydrogen bonds that generally tend to have a low polarizability. And so organics generally have a much lower dielectric constant compared to silicon oxide or something like that. And then the third way is porosity. So what you can do is you can take your dielectric and you can introduce pores in it, okay? And your effective dielectric constant now reduces, obviously, right? Because you have a combination of both an epsilon R as well as air, correct? So you can see here how the dielectric constant can be modulated as I increase the percentage of porosity, right? Going from 0% all the way to, 100% is nothing is there, but yeah, I don't know who made this graph, but 100% doesn't make any sense. It's just air, right? But yeah. And obviously, there's a science that goes into this because you want the pores to be as uniformly distributed as possible. Because if they start clumping up, then you can get channels to the material, right? Which can increase your breakdown and also cause mechanical issues. So, so you need to really you need to really use your process to make sure that these pores are uniformly distributed and they don't kind of clump up so that you can have these kind of channels for breakdown as well as for mechanical issues, right? And here you see how, for different kinds of porous low-K dielectrics, you see that as you increase the porosity, right, and so you're reducing the dielectric constant, you also have a reduction in the Young's modulus, right, the mechanical property. So as you increase the pores and you lower the dielectric constant, things are also getting weaker, so they tend to also break faster, right? Both in terms of dielectric breakdown, also in terms of mechanical breakdown and damage. And I'm not really going into much detail of this, but in terms of porosity, there are many processes you can read up online of how to make pores. So one good example is, I'm sure you've seen this, is an aerogel. And what they do here is they usually mix some kind of silica particles in a liquid, and then they do a process that causes them to interconnect in like a network. And then what you do is at low pressure, you extract the liquid out, so only the network is left. Okay, so you have a network of silicon, which is full of pores of air. So you get this material that actually is, and so apparently it's almost 99% air and just 1% silicon. So it's mostly air. Okay, and it's almost as light as air also. Yeah. And there are other ways to lower dielectric constant, which is rather than just having this kind of dielectric uniformly distributed, even in your transistor, you can keep some open spaces, like here there's air, and then overall the effective dielectric constant is now lower, right? But typically this is not used because it has many reliability issues, obviously mechanical issues, and so on. So typically people don't leave these kind of empty spaces in the cross section. Also, when you do processes like annealing and all that, these things are air pockets. They can expand and cause breakage and stuff, right? So that's concluded. That's it. And so hopefully now when you look at something like this, you can identify where the high K and low K dielectrics go. Yeah. No. So this is the low K dielectric is not electrically conductive, right? So they're not defects. They just make the effective dielectric constant lower. But they are defects in the sense that they lower the mechanical strength of the material, and they cause it to break down much faster. Off? No, we want the pores in this case because we want to lower the K. No. No. Oh, you mean like, yeah, the pores can sometimes occur naturally during the processing, but that is bad. Like that is a different thing, right? In this case, you intentionally introduce these uniformly distributed pores so that you lower the effective K. Yeah.
Oh, we are discussing about the reliability of CMOS. We are actually talking about the reliability of the gate dielectric, right?
Reliability of what?
We are talking about the reliability of the device.
Mhm.
Actually, the most important thing is the reliability of the dielectric.
Yes.
And
But not just the gate dielectric, also the dielectric that goes in different metal layers.
yeah, so when people do the time-dependent dielectric breakdown experiment, basically they just stress the gate dielectric for a long period of time to see when does it fail.
But they do it accelerated. See, like,
By temperature.
yeah, by temperature and by field. So say you want to make sure, so say your usual operating condition is some E, right? Say E0, right? So E0 is your electric field at which it usually operates. But say you want to make sure that it fails only 10 years later, right? You can't do it at E0 because you can't wait 10 years, right? So typically what you'll do is you'll do it at much higher field and much higher temperature. And because it usually follows some kind of Arrhenius relationship, right? The time to failure, you can do it at a higher temperature and then you can extrapolate how the failure would be at a lower temperature as well as field. So that's how they calculate indirectly what the mean time to failure is. You do this accelerated test. Yeah.
And for the okay dielectric, like, what's the typical dielectric?
So it's between 3 and 4 actually. Yeah.
And is that field like ready? When I say field, I mean, is that field of study already saturated? Like people already, like everything is well published?
I don't know. You should ask professor. I don't know if they made any new. See, but the general trend is when you tend to make the dielectrics even lower K, right? They tend to be more mechanically unstable, So like when you are handling because most of these dies are eventually going to be packaged, right? Which means you're going to do some bonding and stuff, right? So when you do bonding, you're going to take the die and apply pressure, right? So if the dielectric is not able to withstand that pressure, it's going to get damaged. So you can't go very low K. You basically do enough to get the benefit, right? The main reason why you want low K is mainly because you want to lower the RC delay of the links, right? Yeah. So this CMOS is generally a lower K dielectric. So it has basically, other than silicon and oxygen, it has other elements also, and it generally, based on the growing conditions, it generally also tends to be porous, slightly porous, right? So this one is generally lower K. While the dielectric here is ALD, it's the best kind of dielectric you can grow, right? That's why it tends to be very high K.
What's the difference between ALD and MLD?
What is MLD?
CMLD.
I don't know. What is that? Molecular layer? No, I don't know.
There are a lot of oxide options for entering.
Mm.
Briefly rank quality of different oxide like which process gives you better quality.
You're asking which oxide you usually use?
Like there are PEC.
Oh,
H.
so generally, right, so most of the CVDs could be plasma enhanced, which means they are done at a higher energy and temperature, right? Generally, when you give the atoms a higher energy and temperature, they tend to deposit with a higher quality because you give them more mobility to move around and occupy the space with lowest energy, right? So they tend to be higher quality. Most of these, that's why here you see this is LPCVD, right? And LPCVD, these are usually deposited at a lower temperature and are usually not plasma activated or plasma enhanced, right? So they have a poorer quality than when you plasma enhance it or when you do it at a higher temperature. Yeah.
Random, porosity. Would not be a problem.
Thermal oxide has random porosity.
Yeah, it doesn't seem like the porosity structure.
No, but your thermal oxide, you don't want porosity in thermal oxide. Generally, thermal oxide doesn't have porosity. Like TEOS, like you're asking, no, it's like a uniform, it's like a very microscopic. Like I'm not really like, to be honest with you, right? I'm not very sure about how the microstructure looks like actually. All I know is that it's lower K because it generally tends to have more defects compared to just thermal oxide, and hence it tends to be lower dielectrics. Okay. Oh, you were saying something?
Different. Oh, so, for LPCVD upright, temperature is usually higher. And for PCVD, because we add the plasma, so that we can provide extra energy, so that we can lower the position.
Mm-hmm.
That's what, I think that's what I'm asking, the outside.
You're saying so, okay, so I don't know which one is which, but all I can say is that when you give the atoms higher energy, right, which means in terms of temperature and enhancing them through plasma, tends to be higher quality. That is also CVD, but I'm guessing it's at a lower temperature.
Yeah.
Yeah.
It's not silent, but
I mean, who cares about the details, right? All that matters is you give the atoms enough energy and temperature, it's going to be higher quality.
so for AOD.
Yeah.
We, in this class, we talk about, thermal dielectrics only for diffusion. But actually, like, because AOD deposition is at low temperature, and like you're not actually not sure about if the precursor and the co-precursor are like fully reactive. So usually after AOD deposition, there will also be a
Annealing step. Okay. Yeah. Okay then. Any more questions? Molecular level. Yeah. Yeah, so this concludes all the classes. So that's going to be project review. So it depends on number of groups. Usually it's like 15-20 minutes. So the presentation will be, so typically presentation 15 minutes, 5 minutes questions. Yeah. Sorry? No, so what I'm gonna, okay, so what I'm gonna do is I'm gonna actually, this Wednesday, I'm gonna take a list of groups and then I'll send a Google Sheet because we need to figure out what days on next week everyone is available, right? Because I'm sure you have other midterms also. So we need to figure out what, huh? Sorry, finals that you have, right? And so we need to figure out a time that works for everyone. Because ideally everyone should be present for, presentations. Yeah.
And you said we 2 days to finish all the presentation, and then we're not doing presentation next Monday.
What do you mean 2 days to finish? This Wednesday and this Friday is basically just like the TA session, right? People who have an issue with the project can come and we're gonna like, because we have a lot of time, we can help you with the project. Me, Vineet and Kritikesh, right? And then next week, we need to figure out 2 days, 2 separate days, 2 hours each for the project presentation.
And next Monday, we're not doing presentation.
We haven't figured out the dates, yeah. It can be any day, it just depends on who is available, right?
Is there a way it's
I don't have that kind of power.